Hello, welcome to this presentation on a new feature within Veeam version 10. This is the ability to protect your network attached storage and the shares that they contain. This presentation is around the operation of that feature. What it isn't is a marketing guide to Veeam or Veeam's NAS protection. It's also not a help guide on how to configure, what buttons to press or what wizard to travel through to enable the backup or protection of any shares. The aim of this is to demystify the technology itself and give people an understanding of how it works. The thought process behind this is, if I understand how something works properly, I can design it, I can make it efficient and performant, as well as understanding the help guides on how to configure and protect my workloads. Prerequisites for this, really easy. Go and get a tea, go and get a coffee, get a snack, comfy cushion, headphones, speakers, sit back, relax, and I'll spend about 40 minutes to take you through this, and hopefully you'll learn something at the end of it that's useful in designing what you need to do. So the agenda itself, we're going to look at change file tracking, roles and component parts of the Veeam feature, technology overview, some traffic flows, one last page on possible bottlenecks you'll come across and how we can look at mitigating those if we can. So let's look at how does change file tracking work. What does it use? Why is it so fast? Because it is extremely fast. It's actually part of a different process which is contained within the cache repository. Although I mentioned the cache repository, it's actually the file proxies that do most of the work on this, but we'll cover the file repository processes a little bit further on. So for now, let's just look at change file tracking. It's actually a Veeam technology. It was written by Veeam from the ground up, which is why nobody else comes close to being quite as efficient at finding modified or deleted files. We're only interested in those changes once we've done a main backup. So this is why at the moment there's no other vendor on the market that can kind of get close to this. So marketing over, let's move on. So change file tracking, what does it do? And a very simple term, within every share, within file shares itself, we've just got a folder structure. It starts at the top level folder, and then inside of those will be a tree of folders and files. The term tree is very useful because we'll use that in how we enumerate and what we do, the processes. So each time we walk that tree and we find a single figure that we'll attribute to the top level folder. So it's on every time we run a backup. So the first backup will create this database of information. So let's look at it constructively. If I've got a share and it has 5 folders in the root, then I'm going to have 5 entries in my database. If I've got 50,000 folders in the root, I'm going to have 50,000 entries in my database. So every NAS, every file share is going to have a different structure with a different count of folders. However, because we're only interested in that top level folder to start with, it means that we can actually be really quick about how we're doing things. So how do we do things? Well, we interrogate that first level folder and we look at every folder and every file it contains. And we look at the file names, the creation times, the modified times, and the security info. From that, we put all that together and we create this single hash sum that we put onto the first level folder within the share. Once we've added it to that first level folder in the share, then we need to make sure we've stored it for comparison at a later date. So we create this vcache, and the vcache itself is stored in the cache repository, which again, as I said, I'll cover before. So depending upon the number of first level folders will depend on how many entries I'm going to have on this. So how does that actually work in reality? So in reality, as I've now done my first backup, I've got a list of all those folders and hash sums. And the next time I run, I'm looking for any changes that occur in this. So I'll start to enumerate or walk the tree of that top level folder again, and I'll create once more another hash sum. I'll then evaluate that hash sum with the contents that I have in the vcache on the cache repository, and if they're the same, I'll just drop that process and move on to the next validation. So that's good. That means I can actually work my way through folders. Again, if I've got 50 folders and only one folder contains a change, then very quickly I can dismiss 49 folders and start to work on a single folder that has some changes or modifications inside them. So once I reach my folder, I walk that tree and I look out and I try and find my hash sum. Once I've found the hash sum, I'll add the two and compare them, and I'll realise that actually they don't add up. So I'll flag this for more interrogation. So the cache repository will say to the file server, go out and find more, the file proxy, sorry, find more information. So we take the source data, and once we've taken the source data, we'll look at the same metadata in the name, creation, modified date, size, types, and we'll compare it to the metadata of the last backup, and we'll look for those differences. So again, very quickly we can find the file in this occasion, because I've only got 3, that is different from the last backup. Once I've found that file, then I can just process it and I can protect it in my repository. Once I've protected it in my repository, I now create a new hash sum for the first level, for the top level folder, and I'm going to write that down into the vcache on the cache repository. So we stop for a quick breather. What you've kind of understood from that is, very effectively, we can parse and walk the tree of every single folder that's a top level within the file share. We can very quickly rule out the folders that have no changes or no work to do on them, and narrow down to files that have changed or been deleted in a very short period of time. So this is why change file tracking is so important. So let's look at a few components of the NAS and how they go together. So I mentioned the cache repository, so we're going to talk about that. I mentioned the file proxy and kind of mentioned the repository. So similar names for those people that have used Veeam before. However, they do slightly different jobs. So in the case of cache repository, it's a completely new function within Veeam. The cache repository is only used in the NAS jobs, and it's actually quite crucial in the incremental backup due to the nature of how we process things. Another interesting feature of the cache repository is it is the master agent for the NAS jobs. So in standard Veeam backup and replication, the VBR server itself controls the scheduling and the communication structure down to the repositories and to the proxy servers. Within NAS backup, we've given that job off to the cache repository. So the VBR server tells the cache repository what it wants, and the cache repository will go out and do the rest. So all communication flows go through the cache repository. It's also used in the restore process as an obvious. If it's the master agent and it stores the vcache, then the reverse procedure is very effective if we use the cache repository as well. Because of this, the ideal is that it should sit as near as possible to the file proxy and the source data, because what we don't want, Veeam is a software. As a software, it means that we can utilize anything that you can throw at it. If you give us 10 gig, we'll try and use 10 gig. If you give us 40, we'll try and use 40 gig. Whatever bandwidth is out there, we'll try and consume. If we sit closer to those devices, it means there's less chance of other traffic causing us issues, and we can do our job very effectively. The use of fast disks is also not an essential SSD. If you think about what the cache repository is going to do, it's going to store the vcache. So as I mentioned before, if you've got 5 files in your vcache, 5 top level folders, it's going to store 5 entries. If you've got 50,000, it's going to store 50,000. So it's a case by case basis. However, the vcache is created per job. So if I have a single job to protect a NAS, I'm going to have 1 vcache. If I have 50 jobs, I'm going to have 50 vcaches. If they're all running using different proxy servers, different repositories, then there is going to be interaction on those disks. So fast disks, yes. Do they need to be super fast? Not really, no. However, it should not be part of a scale-out backup repository as far as where those data are stored. As the name implies, it is a repository type. It is inside of Veeam backup and replication. The role is repository. So we can designate that it is part of a server, but we don't want it there whatsoever. It will not perform if we put it inside a scale-out backup repository, so please don't. So how does it kind of function? Well, we have the cache repository, and as I said, that's the master agent in charge of the file proxies to tell them what to do. So inside the repository, we need some RAM, and we need ample RAM to map out to whatever we're going to consume as far as the vcache is concerned, because as mentioned before, the vcache is going to live inside those high-speed disks. However, when we get a job to run, what will happen is VBR tells the cache repository what it wants. It will go to the file proxy. File proxy will come back after it walks that tree and finds those hash sums out. Those are stored inside RAM in a metadata file, and then the metadata file will then do comparisons against the data that's stored in the vcache. If everything's okay, that process will drop and the next hash sum will come in from the file proxy. If there is a mismatch, then that's simple. The cache repository will then tell the file proxy to go out and interrogate the source data and interrogate the metadata from the repository and find the missing or the modified or deleted file. So in a nutshell, once we've done that, we're left with a new hash sum, which is then processed and gets written down into the vcache, ready for the next incremental. So the cache repository, how does it actually work? At the end of the day, this is kind of supposed to be a deep dive, so let's look at how that actually works itself. The cache repository receives an order from VBR server through the scheduler to start a job. The cache repository will look out and look for a file proxy server. In the case here in my slide, I've got 4, but it doesn't really matter. It will just find one. Doesn't care which one it is. It will just say, go and tell me what I've got. That file proxy will go and interrogate the share, and it will come back with information, and it'll say, I've got 4 root level folders. The cache repository then distributes those root level folders out across all the file proxies that are available to it. And luckily enough, we've got 4 folders, we've got 4 proxies, so each will receive a folder to enumerate. Each file proxy will then walk the tree on their specific folder and move on to any other folders that are free and available. When it comes across data which has been modified, then the file proxies themselves will start at the bottom of that list. So we don't start at the top and work our way down, we start at the bottom and work our way up, and it will start to process and send those modified or deleted informations into the target repository on very simplistic processes. As you can see, this is a very simple way to work. Because it's simple, there's less to go wrong, and it's also more efficient and very performant. So, in summary, the cache repository stores a single vcache per job. More jobs, more vcaches. It's the master agent which coordinates all the workloads with the file proxies. It doesn't store any version or deleted metadata, and it is part of the restore process when we're restoring files back into the what then becomes the target production environment. Another thing that I do get asked is what happens if the vcache is actually lost? It's very simple. If the vcache is lost, the next time the job runs, it will walk the tree again on the structure that exists there. It will look at the last backup, the metadata that was run, and it will rebuild the last vcache and write that down. It doesn't force any new full backups or any backups that are not warranted to be full. So if no file has changed, that file will not be re-backed up. We just rebuild the vcache. So let's look at the file proxy. What's different because we have proxies already? So currently we have 2 different types of proxies. We have Hyper-V and VMware proxies. I suppose 3 if you want to count AHV. However, within the VBR console itself, we tend to see only one, and that's the VMware proxy. Hyper-V contains its own proxy. It is by definition its own proxy, and the same AHV has its own proxy inside its own hypervisor. So what's different about this one? Well, this one actually works extremely hard. If you think the cache repository is going out and saying, enumerate this, go and walk that structure here, go and pull the metadata from the repository and compare it against what I've got in my source data. So it can be resource hungry, which leads to another question of, does it need its own resources? Veeam as a non-complex product has very limited requirements or very low requirements for resources. So we need proxy servers, we need repositories, we need a VBR server. Now we need a cache repository, but it's still a repository. By growing our infrastructure, then we can very easily scale out performance and efficiencies. However, is it really needed? Because the question is that if I have a medium-sized infrastructure and in the evening or in the middle of the night, I'm protecting and backing up my virtual infrastructure and my hypervisors, then what's the machines doing during the day? So my VMware proxy that's hard at work at night isn't necessarily hard at work during the day. So can we make that a NAS file proxy? Because the impact to production on the file proxy can be limited. We can actually use a form of quotes, which I'll cover in a while, and we can we can throttle how fast that accesses it. And the impact onto a file proxy is generally not as severe as what if I was protecting and taking a snapshot of your SQL databases, then there could be impact. If I'm doing that, if I'm backing up files on a file proxy and a file share, am I going to have that same impact? Probably not. But take it on a case-by-case basis. There is no yes, there is no no. Some people will be able to use the file proxy and the VMware proxy to do the jobs at different times. Some people won't. The resource requirement is slightly higher on CPU, so take that into effect and build your proxy based off the highest known requirement, not the lowest. So the repository, what's new in this repository? There's nothing really new in this repository. It's RAM hungry rather than CPU intensive. The reason being is we write files down differently to the NAS repository, the NAS backup. So we use blobs and metadata to write files down into there, which has already been processed. So it's kind of more of a write machine than it is a CPU intensive machine. So that's the main difference. But there's no reason why a normal Veeam repository for your hypervisor VMs can't be used as a repository for your NAS backups. No reason whatsoever. So let's look at the technology that sits behind there. The first thing we'll look at is threads. What's threads? The thread count just refers to how many things can I do at the same time on a CPU. How much can I actually process? And do I need to process those? So if we look inside the setup when we're adding our network attached storage share, because we add on a share basis, and I said this wasn't a wizard driven thing, but here's just a picture of what the wizard looks like. Anyway, when we're going through the process of adding that file share, we come across this page. This is the backup IO control. This gives us control over how intensive we're going to be across your file share. It starts, there's 5 settings. There's the one in the middle that you can see now with a little blue tick in it, and then there's 2 to the left, 2 to the right. Lower impact, faster backups. So we'll start right on the left hand side, which is the lower impact. What does that mean? There's actually 3 components to this. So even though it might not make sense here, by the time we reach the end, hopefully it'll make sense to you of why this is really effective. So on the lowest setting, I can use 1 thread per proxy task. We'll cover proxy tasks, so don't worry too much, with a maximum of 1 proxy. So 1 thread, 1 proxy. So in my picture before, I had 4 proxies. In reality, in this setting, I would only ever use 1. If I go to the second setting, which is in the middle of the blue and the furthest left, I now increase the thread count to 4 threads per proxy task, but I'm still limited to 1 proxy server. So 4 times faster can I process, but the limitation is still there. And it's funny because that's below normal. Normal is 8 threads per proxy task with a maximum of 2 proxies. So it isn't actually that much more. What I would take away from this is quick, this is fast. So even at 4 threads on a 1 proxy below normal setting, you're going to get speed. As a normal 8 threads per proxy task with 2 proxies, that's 16 threads you can have running. If you imagine your file services that you've actually got running on the NAS itself, then you've got production data that's running through there as well. So these threads are going to impact that production data because we're going to be asking for more information. So by using 1, 4 or 8, we can actually reduce down the amount of activity that we're going to apply to that, so we can control the impact into the file server, the file share itself. If we start to look at above normal, then we start looking at 16 threads of proxy with a maximum of 4 proxies. This is kind of like, wow, this is good. This goes back to my picture of the 4 proxies and the 4 shares underneath. It sounds Like, it's really good. However, this is actually more CPU intensive, as you can imagine. I've now doubled the amount of threads per proxy task, so my CPU is going to be working a lot harder. I can now distribute that across 4 proxies, so I can get a lot more. The impact to your network when you start looking at this is we will take whatever you offer us. If you cause that bandwidth down, that's absolutely fine. If you restrict the threads down to 8, that's also fine. But we will take anything across those 4 proxies that you try and give us. And the last setting, which is right on the far right, faster backup, this is 16 threads per proxy task with no limit on the number of proxies. This sounds really good, because why don't we just set this anyway and we'll saturate the proxy servers and the CPUs will just run them, but I'll just get loads of backups. Well, let's look at it in a different way. If I have 10 proxies, each with 16 threads on a task, I've got 160 threads that my NAS has got to deal with, or the controllers, or whatever it is that you're using for the network attached infrastructure. 160 threads is going to have a big impact. We're going to hit a different bottleneck type before those 160 threads are reached. More importantly, this is out of control. It's out of your control. This is a set and forget where we don't really care, because whatever happens, happens, but do it as fast as you can. Nobody ever wants that in an infrastructure. We want to control the minimum settings, but we also want to control the maximum settings, so that we know that any surrounding processes within the whole infrastructure still have the ability to operate. We want that control. So it's there. There's an ability to use it. Would I? No. The normal thread count, or the default setting of 8 threads and 2 proxies, is actually a really, really good setting, but test it yourself. There is impact to the proxy served, the file proxies. Test it yourself in your own environment. Start with a normal. You can always turn it up. Make sure that it meets the requirements of your organization. So I mentioned there was 3 items here in backup IO control. The second item is throttling units. So basically, how many throttling units per share am I allocating? So at the moment, on the lowest setting, we've got 40 throttling units with a maximum of 1 proxy. And the below normal is also 40 throttling units with a maximum of 1 proxy. And again, in a minute, I'll show you a calculation which will show why those are calculated differently as an end result. If we look at the normal, then we move up to 80 throttling units per agent with a maximum of 2 proxies. And remember, the last one was on tasks, this is now on agents. Above normal takes us to 160 throttling units per agent with a maximum of 4 proxies, and then the highest is 160 with no proxy limit. So again, please remember, the highest setting will run out of resources before it runs out of anything else. So just because you've set it to the highest doesn't mean that you're actually going to do anything any better than if you set it to above normal or normal. A lot of dependencies. The last is the backup share throttling unit count, and this is where these start to come together, because on the lowest setting we have 10 throttling units per share. On the below normal count we have 40, and then as we go into the normal count we have 160, and if we look at the above normal we have 640. Now above normal and highest is going to be the same, so that's why it's not included here. So if we look at where those are actually applied and how to look at them on a basic value. If I have the normal value, which is 80 throttling units per agent, however my share only has 160 throttling units in total. Now I've got 2 proxies in that normal setting, so that's 2 agents I can run, 1 on each. So if we add those together, I have 160 divided by 80 per agent, which gives me a maximum of 2 proxy servers. So you can see that the maths behind it is actually quite simple to work out what the maximum that you can achieve in any way, shape or form. We've done it for you. It's lowest, it's below normal, normal, above normal or highest. But the maths is really simple. We throttle. How can we throttle? That's what we're limited by. This is where the outputs are. So if we look at how this comes together then, it's quite simple. Ignore the writing on the other side. Let's look at just the picture. We have a task. The task comes down from the cache repository, hits the file proxy. The file proxy starts a task. The task initiates a Veeam agent process, and that has all the threads that we've just talked about in the last couple of slides. So by default, we have 8 threads in that agent process and in that task. So going back 3 or 4 slides, how many we can have per proxy per task, and how many we can have per agent. Throttling per agent, the amount of threads per task. So I've got 8 threads here. The threads themselves can be split into multiple jobs. So we have threads for walking the tree, and that will be high CPU utilization because I'm going out and all I'm trying to do is work out hash sums so that I can send them back to the cache repository. And then we add the file transfers. The file transfers are putting that information together, what I have to send across. So we're going to use more RAM for the file transfers to make sure that all that data gets processed and it streams correctly. Now, when we start a job, what will happen is all the threads will be consumed by walking the tree, because we need to establish what those hash sums and what needs to be transferred. Once we've got to the bottom of the folder level and we have a top level folder, we can send that information back. If there's changes, we can start the file transfer straight away. So in some circumstances you'll see this running, and you'll see that the actual enumeration, the hash sum creation, is taking time. And this will start to crank up and do that, and all of a sudden the file transfer will start. What this means is I've now walked enough of the tree and created those hash sums to validate them, worked out what needs doing, and now I'm telling that the file transfer service to actually start doing some transfers. So let's have a look how it works. So a single file proxy has a single Veeam agent process on it. So real simple maths here. One file proxy, one task, one Veeam agent process. However, a task can have between 1 and 16 threads, as discussed earlier on. So it can get a little bit more complex. So if we look at it as example 1, it's a very simple job. Job hits cache repository, the file proxy takes that, it creates a single task, which is a single Veeam agent process that has multiple threads. There's only 2 showing there because if I put 8, it'll look scruffy. That goes and processes a single share and does the workload on the top. Great for small jobs, and you could in fact on here take that down into below normal settings and it would work effectively. If we look at kind of some standard jobs that we start to see, so multiple shares in the same job will create multiple tasks. So even if I've got one file proxy, my cache repository that's linked to it will say I want you to process 3 shares. So it will create a task per share, which contains a Veeam agent process per share and its own threads per share. So we can start to scale by using multiple shares in a job. However, our limiting factor there is still that file proxy. So remember, when we set our jobs and our backup IO control, that's on a per share level as well. But this is good for medium, but I'm still restricted by a single file proxy. So if we really want to start looking at scale, we need multiple file proxies. So this setting here would be at the above normal level because I have 3 proxy servers. So my job, my cache repository, distributes the load to 5 different file proxies, and each file proxy will create a single task, a single Veeam agent process, the amount of threads that's allocated, and it will process a share itself. So the file proxies won't work across the multiple shares because each one is more effective doing its own share. But now we've got that ability to scale across the multiple file proxies and share the resources with nobody else. So better workload efficiencies if we do it in this way. So in summary, each Veeam agent process and each share can only have one task. Only one Veeam agent process per file proxy per job. Up maximum of 160 threads per Veeam agent process and task. However, do you really want to get to that limit? Try to stay at a maximum of 4 proxy limits, regardless of anything. If you're going to scale out on jobs, create new jobs, create jobs across shares. Let's start to distribute that loading across multiple proxies or multiple shares to increase the number of threads, but watch out what your resources are in your infrastructure. If you don't have the right resources, you can set this to the maximum, and literally it will soak up anything that we can get our hands on to move that data for you. So you do have to understand your own infrastructure, as well as what Veeam can do with it. So let's have a look at retention. We've got three different types of retention: short-term is secondary, and archival retention. The archival retention is a new type of retention, but let's have a look at the short-term first of all. The short-term retention is actually just a mirror of the source data regardless of the retention policy. So the retention policy controls version retention, not file content. In a standard backup, we kind of say, okay, back up this virtual machine and the contents of the virtual machine, and then we say, okay, so after 30 days retire that backup. And if it's part of an incremental process, all we'll do is we're kind of deleting one to create a new one, so we can contain our retention to 30 days, 60 days, whatever it might be. And NAS is slightly different, because file shares, generally data doesn't get deleted. So if I was to delete and keep doing incremental backups, all I'd be doing is adding processing and everything else. So the reality is that if I put something in my file share, then if I'm protecting it, I need to keep that protection as long as it's in the source. So I don't need to age them out. What I do need to take care of and to manage is the different versions or modifications and deletions that occur within there. So we have retention policy that controls the version and the time. So in short-term retention, we're controlling a time that the amount of versions will be stored. So you said 30 days. In that 30 days, any versions, any modified, will be stored in that 30 days. We can choose a scale-out backup repository as a location to put this data. However, at this moment in time, if you've got the capacity tier in there, it will be ignored because we don't want to send things to object storage and split it up at this moment in time. So standard scale-out backup repository with multiple extents. Even if it's actually much better in some circumstances, if you have a scale-out backup repository with more than 2 extents within that repository, then we actually distribute metadata and replicate it across the extents for resiliency. There's currently no option to use tape or object storage as a target. So let's again go back to that. What do we retain? So the NAS data and short-term retention data is a full copy. My retention policy is 21 days, and I get multiple versions over the period of those 21 days. So on day 26, if we go and have a look, then actually the full data is still there. However, version 1 and version 2 is now deleted, and all I have is version 3 and version 4. So I still have full data, less the expired versions. Simple. So secondary location. So retention type has an option to store something somewhere else. A secondary location is the same as a backup copy job in Veeam backup and replication. We take the data that you protected and we copy it to a different location. On top of this, we can actually have our own retention policy. However, because it's a backup copy job, it does appear as a backup copy job as well. Inside of VBR, you will see it as the name of the initial job, be it the NAS backup, with the in brackets copy added to the end of the name. So please don't edit that one. Go back into your initial file backup job and edit the secondary locations or options within there, because otherwise it's just going to get confusing as you flip forward and backwards, because you're going to change the backup copy job and not understand the effect that it's actually had on your primary job. So as for secondary location, you can't use object storage still, but sober is an option, as is in the primary one. Main key here is that the secondary location can have its own retention policy. So if you think about how we tend to look at protecting data, we tend to store short-term retention in a local storage area, which is normally faster disks because we want to be able to process that, and then our secondary data to be part of the 321 option, which I'm not saying is what we're doing here, by the way, but we will move that to a different data center, a different media type, etc. So in this case, actually, we want to have its own retention policy, that's different from the first. So the first, as we said, 21-day retention. Well, your secondary location could have a 6-month retention. So we can control very well how we retain that data in the secondary location. The third option for retention is the archive location. So the archive location, it's a new type of option, and it's only available in NAS. What we store here is versions and deletions only. So we have a choice. We also have its own retention, funnily enough. However, so we can look at filtering versions, deletions, or extensions. So we can keep deletions and versions for multiple either numbers, but we can control them differently. So we can say versions, I can have the last 10 versions, but deletions, I only want the last 3 deletions. Extensions. With extensions, I can stipulate that include a specific extension or exclude specific extensions in those version controls. So the simplest way to look at the archive location is if you have an ISO file, we place the ISO file into a nice little folder that's in our network attached storage, and that's where it will live. So the short-term backup, as I said, is a mirror. So that night it will back up that ISO into short-term retention, and it will live there for the life of that job, regardless of retention. However, the one thing that we know is we will never change an ISO file. It's an ISO file. So therefore, it will never move into archive as a version or a deletion unless we delete it. And we could, to be honest, when it comes to ISO files, you probably exclude those as part of the extension options in archive anyway, because they don't change. What's the point? An ISO is always replaceable from somewhere else. So previous versions, these are the options that we have for keeping the previous version. We have to enable it as a starting point. It's not enabled by default. As soon as we enable archive retention and we set our own policies, then the start time for that retention starts immediately. So let's say that I create a Word document today and I put it into my home share, my home folder on my share. That night it backs up the home folder, puts it into the short-term retention repository. The next day I change the Word document, and that night it will run. It will see that file's been modified, so it will change. It will store the new version of that. When it stores that new version, I then also have my archive version, which has a retention policy saying store 10 versions of this for X amount of time. It says, I've got a version here, so it will then copy that version into my archive file, and the clock starts from there. So whatever that timer is on your archive starts from the time it's backed up, which would be that day. So it can be, it sounds a bit confusing, but it's not. It's quite simple to understand. The main thing is archive location doesn't store production data. It only stores versions and deletions, and anything that and obviously excludes anything that you've told it to be. Archive data, people want to store on different storage types. However, at this moment in time, we don't use immutable storage because the object it might look like it's actually been locked by the immutable storage, but it isn't. So please be aware of this. You can store it in immutable storage, but it isn't going to be immutable. So versions or deleted copies are moved to the archive tier on the next incremental backup. I think I've already just mentioned that anyway. Files are retained depending upon its own policy, not the short term, not the secondary. So of the 3 retention types that we have, each has their own policy, which gives you granular control over where and how long you keep that data. And I mentioned already, it's possible to have multiple copies in both short term and archive. It only applies to versions, obviously, because deleted files will only be in the archive repository. When the short-term retention policy expires a version, it's not classed as a deletion. If we think about version control and deletion control, then we think, okay, so if I'm on day 22 of a 21-day retention on short term, I've just deleted the version, so therefore, will I archive that? And the answer is no. What we're interested in is deletions that occur on the production or source share. So anything that takes place in short-term retention is not classified for either archive as a deletion or a version. Sizing of archives are really difficult. As it's a new structure, it's actually quite complex, because if I'm going to turn around to you and I say, okay, so how often do you change files? How often do you delete files? How long do you want to keep those deletions? How long do you want to keep those versions? Then the blank stares and the empty eyes are very, very common. So we have to, and you have to take this in account when you're actually building this. Unless you have an accurate understanding of your infrastructure about version control and deletions, which, to be honest, I don't know anybody, I've never met anybody that does, you're not going to be able to size this 100% accurate. What you can do is have an understanding of approximations. Once we've got approximations, we can start to look at how much do we need to store in there and how long for, what's important, because it's not the full production, it's only changes. So take that into account. It is important to understand that archiving locations are not going to be as accurate as standard short terms or secondary locations. So, bit of a summary. The short-term repository always holds a copy of all protected files. Regardless of the retention policy, if it's in production and it's been protected, it will always stay in there until it's deleted. Expiration policies only apply to versions, nothing more than that. If you delete a version within the source, it will change, it will be deleted and moved to the archive tier if you have the policy set. If you don't have the archive policy set and you delete off production, then it will still have the same retention policy of the short-term retention, which again, in my case was 21 days before, and that deletion will disappear. So again, moving stuff to the archive repository will depend on the archiving policy, not the short-term policy. Please remember that. So a quick look at some job flows. No animations here because I just don't see the point. You can follow numbers, nice and easy. This is if you're going to use an SMB repository. The reason why I mention SMB repositories, some people still use them because they've got bits and bats of old technology lying around that they find is useful for this. When we use an SMB repository, we actually use a gateway to send data into that repository. It tends to not have its own processing power. Because of this, the job flow is slightly different. So we cache the request standard. We've covered that off in the cache repository. The file proxy sends the hash sums to the cache repository, compares it to the vcache. The vcache quite happy. The cache repo instructs the file proxy what to retrieve, if anything. The file proxy will use the SMB gateway to send the data to the repository. Now, generally what happens is within Veeam, if you leave the option of selecting a gateway for the SMB, it will choose the file proxy that the job's running on. So in our case here, file proxy 1 is also the gateway. So it brings two kind of stories in. If I'm the file proxy and the gateway, it means that I can use the internal bus to send data through to get it to the target repository. Big tick in the box. However, if I'm file proxy 2, I've got to send my data into file proxy 1, which then has to be sent through the gateway into the target repository. So file proxy 1 is actually going to consume more resources. But it doesn't mean it's going to be slower because it's got one less hop to get to that gateway. But it will work in this flow. So both file proxies communicate with the repository, blah, 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 blah. And once all the data is in the cache repo, we write back down to the vcache. That then sends information back to VBR to say we've got a complete job. Now, if you remember at the beginning of this, which was quite a while ago now, I said that sometimes you're going to have locked files that users are using that we can't get to. If a file's locked out, we can't protect it. However, at the end of every job, if you've configured email, then you will receive an email at every job anyway to say success or failure or warning or whatever it might be. But inside that email, you will also get a log of all the files that we weren't able to back up. So you can have a list of files that were open. Now, I'm not saying that you read this every day, but every now and again, if you look at those files, you can find out whether a user has a file open and hasn't shut that file down for months or for days or for weeks, and it's not been protected. So quite quickly you can pull together an information log to say, you know what, this machine needs to be looked at. We need to interrogate this to see what we need to do further with it. So we do actually send you a log to say what hasn't been protected, if anything is out there. So standard repositories, it's a very similar process. The only difference is number 5. So in standard repositories, be it Sober or any other form of target, then each file proxy will send its own data directly into the target repository. So in SMB, there is it valid, is it not, is it convenient, does it work well, because we've got one less hop from the file proxy. Here, definitively, it will work well if your resources are done well. It's a direct out of the source NAS into the file proxy, out of the file proxy into the target repository. Once the job's done again, we'll write down the V cache, all metadata, version data and deleted data put into the repository, and then we send back the same report log or information to VBR, and you'll receive your email with everything that's locked inside it. So one last page, just theoretical bottlenecks. So if we look at where could we see issues, so source data hardware, how busy is your NAS or the file share? If you've got a really intensive unit which is kind of working its hardest anyway, then that can affect the speed that we can process or walk the tree. As I said, it's CPU intensive from our perspective to enumerate every single file and folder that's on that file itself. So that can cause an issue. We will tell you through the job where the bottlenecks are. Veeam is brilliant in the fact that every single backup we do, we will say where we see bottlenecks in that particular process. File sizes will range. So if we look at the different types of files that we can have a 1 kilobyte text file that contains millions of pieces of data, but it's still just a text file created in Notepad. Or we can have a media file that's gigabytes, terabytes in size. So depending upon the file size, most organizations will have a mix between small files and large files. Nobody ever really has all large files or all small files, but we do come across some, funnily enough. So be aware of the size of the files that we're trying to process, because they'll affect the resources within the file proxies. As I said, when we're transferring files, we're more RAM hungry. When we're processing the folder structure and walking the tree, we're more CPU intensive. So bear that in mind. Scaling. SMB source, limited in connections. SMB is much better. So look at your source and what can we do with this source. If we do find that our source is really slow or we're limited with connections such as SMB, then look at scaling out using more proxies, more jobs. Give more options going in to try and fan out the services we're offering. File services. If we can do Windows file servers, and the benefit of using file services as a source of data is we can use VSS. So it's a massive positive in the fact that locked files are less likely to be an issue. However, what we can find is sometimes that can be slower. The reason is that when we do a file service backup, then the actual process doesn't use a file proxy as we know it. What actually happens is we establish a service on that file server that is the file proxy. So if we've got a file server, a Windows box that's basically resource hungry anyway, and we're going to back that up, then the file proxy is going to be slow because it isn't going to have the resources that it needs to do all the processing. So if you're looking at file services, make sure your file server has ample resources to take care of the file proxy and what it's going to do. NFS source, single share jobs can be a bottleneck, as I showed that, where we can scale out so we can have multiple agents across multiple file proxies against multiple jobs. Look at what do I need to back up my job more efficiently, how can I make it? Because what you don't want is, you don't want everything backing up in 10 minutes, but that 10 minutes everything else stops. So you're looking for that happy medium of how I can back up efficiently and performant without killing my production, without causing problems elsewhere. So we can do this by spreading the jobs out, by doing multiple shares, more shares in a job. So there's lots of different options. Be aware of those options and when to utilize them. And last lot, if you're going to use an SMB repository, it will be a single point of failure because we're using a single gateway server. And as I mentioned, in an SMB repository, we can either set that to automatic or we can stipulate a chosen machine. If we choose a machine, okay, but it still means that however many file proxies you're using have only got that single access gateway server. So we'll try and, again, design around that. So this is end of part one. This is, when I say end of part one, end of episode one, this is Veeam network attached storage operations, finished and done with. I hope you enjoyed it. If you do need any further help, please reach out. My information is on the front of the deck or on the video. So have fun and thank you very much and enjoy the day. Bye bye.